And we are live. Sanbonani Dumilang, good morning. Goeiemorgen. Welcome to day 131 of lockdown to Mill Park Business School's next episode in our Tomorrow's Beautiful webinar series. And today our guest is Andre Krokamp, director at Mindburst Workshop, and he's going to enlighten us on neuroscience, the fourth industrial revolution, and the life of work. And folks, prepare to be amazed. So just a quick introduction. Andre is a fascinating individual, and for most of his life has been working as an educational media developer. His first degree was in theology at Rhodes University, and later completed his master's in cognitive archaeology at WITS, where he explored the origins of symbolic thinking in humans. And Andre's interest in neuroscience and the study of human sensation, perception, emotion, memory, and cognition took him to the Amazon jungle. Can you believe it, folks? To the Amazon jungle, where he worked with the shamans for 6 months to explore the use of mind-altering plants. Absolutely fascinating. And Andre is also a human rights activist and also designs and develops museums all over the country. Absolutely interesting, isn't it? Folks, with that, and it's because Andre is our main feature today, I will stand back, and Andre, I'm handing over to you to enlighten us. Looking forward.
Thanks, Kobus. I appreciate that. Right, Michaela, let's have the first slide. Here we go. Okay, great. Right. Well, I'm sure you all know what this is. This is COVID, bastard. But did you know that it was actually an artificial intelligence in Canada called Blue Dot that first identified the potential of a new pandemic spreading from Wuhan in China? It did this more than a week before the CDC and WHO recognized the threat of a new coronavirus. Now, the AI Blue Dot even predicted the countries the virus would spread to in the correct order. It used natural language processing and machine learning to cull data from hundreds of thousands of sources, including statements from official public health organizations, digital media, global airline ticketing data, livestock health reports, and population demographics. And it does this every 15 minutes, 24 hours a day, and then a group of physicians and computer programmers review the findings and create reports. So welcome to the era of machine learning, the fourth industrial revolution. And while we're going to contemplate the impact of the fourth industrial revolution on work, we always have to see it in combination with the effects of other global challenges like economic inequality, climate change, and communicable diseases. It's quite interesting that very few companies are using machine learning at the moment, but with lockdown and the coronavirus, many small businesses have become more interested in how to integrate AI and machine learning. Thanks, Michaela. Next slide. I'm going to assume that you already know something about the different industrial revolutions. If you need clarity, we can come back in the Q&A session. The fourth industrial revolution is an era driven by the development of machine learning for the purposes of modeling complex systems, manipulating big data, integrating the Internet of Things, driving the role of algorithms in our daily lives, including surveillance, and automating jobs that were once done by humans. The fourth industrial revolution is also characterized by the way machine learning has changed the following fields. And if you're willing to work with AI, these are growing fields at the moment in the world: genetic engineering, synthetic biology, 3D printing, virtual reality, augmented reality, quantum computing, and space exploration. It also includes the radical merging of human biology with technology and the ability to manipulate the fundamental building blocks of reality through gene editing technologies like CRISPR. And in fact, I don't know if you've seen, a Harvard geneticist has just released a plan to genetically engineer humans so that they can be fit for life on Mars. And other editing technologies, including nanotechnology, that can produce molecular machines and programmable matter. Now, when technology changes the way we work, learn, trade, play, and live, we call it a disruptive technology. And that's what we're going to explore today, is how this tech has disrupted the world of work and is challenging us to redefine what it means to be human. What should be sobering for us is the fact that while many of our educational institutions are still trying to turn human beings into poor computers, some machines are learning through trial and error and can perform many complex tasks better than human beings. Can we go to the next slide? The most important and perhaps obvious thing I'm going to stress is don't choose a job a robot can do better than you. In other words, don't choose a job that focuses on memorizing content and performing step-by-step procedures. Machines are already better at this than you can ever be. So graduating from your studies with the skills of a poor computer is not a strategy for surviving in the 21st century. In 2017, Google's AI AlphaZero learned to play chess from scratch by playing against itself with no other information other than the rules, no examples of games, no other players, no opening theory or end-game table bases. After only 4 hours of self-learning, it beat the top 2016 chess engine Stockfish 8 in a 100-game match. It surprised the hell out of me, said Professor Jonathan Schaefer, an AI researcher at the University of Alberta, who's built some of the world's strongest chess programs. He said, the games were beautiful and creative. AlphaZero made apparently crazy sacrifices that humans would never even consider in order to get more freedom of movement. But it also played differently to all other chess programs, which rely on human input. What is more surprising is that it made moves that no human had ever made in 1,500 years of chess. Next slide. Self-driving cars can see 360 degrees. They don't get hungry, angry, tired, drunk, or horny. And they are going to replace millions of drivers all over the world. But we're not just talking about automation replacing long-distance truck drivers. Miners, factory workers, street sweepers, farm laborers, domestic workers, cashiers, tellers, and clerks who do menial tasks. We're talking about machines that can do the work of telemarketers, bookkeepers, personal financial advisors, stock traders, paralegals, insurance underwriters, real estate agents, editors, printers and publishers, travel agents, diagnosticians who can identify disease, pharmacists who fill prescriptions, journalists who follow predictable writing formulas, website designers, military pilots, and highly obedient soldiers. Being able to code is a huge advantage in the fourth industrial revolution, but understand that if all you can do is code, people who are younger and faster than you and who have played more complex computer games than you will always be willing to work for less than you. If you can do something more, like perceiving patterns in the data and interpreting statistics in order to develop an hypothesis about what's going on, and then represent that information meaningfully for the human senses, you have a very valuable skill. And the field of data science is growing very, very fast. If you're going into a traditional field like engineering, architecture, accounting, law, medicine, pharmacy, you first need to recognize that research will always be more important than practice. If you do go into practice, you will need to learn to combine deep knowledge of that industry with the latest analytical tools and work together with an AI in order to quickly adapt and stay ahead of the game. Next slide. Machines are fast. For example, the US Department of Energy's Oak Ridge National Laboratory announced that its supercomputer Summit overtook China's Taihu Light in speed, reaching 200 petaflops. I don't know if any of you know what 200 petaflops means. It's basically a gazillion. To put it in human terms, 200 petaflops is approximately 6.3 billion people making a calculation every second for an entire year. That's what Summit can do in 1 second. Supercomputers like this can work with huge data sets like genetic code, make predictions for complex systems like weather, crack encryption codes, and run complex simulations. Machines are fast, but they're not as complex as our brains. Human brains are slow, but they're the most complex objects in the known universe. Next slide. So what human skills will be valued in the fourth industrial revolution? So according to the World Economic Forum, these are the skills that are most highly valued. And you can just have a look at this list. I'm not going to read it out, but what you will notice when you're reading it is STEM is not there. Science, technology, economics, and math doesn't appear. These are the skills that are going to be valued. We can talk about the future of specific jobs in the Q&A later, but what I want to emphasize before going further is that thriving in the future is no longer about having a career. It's about having a set of thinking skills that can be used in many different fields. The idea of a single and clearly defined career path is being replaced with the need to develop a more multi-skilled ability to embrace the ability to many different ways of making an income, requiring you to become a diversely talented, multidisciplinary, collaborating, shape-shifting, long-life learner on the move. The speed at which technology is now changing, and as a result, the speed at which our knowledge of reality is changing, has never been this fast. In fact, Deloitte said that the half-life of a skill in my generation, and I'm now 56 years old, when I left school, the half-life of a skill was 26 years. In other words, after 26 years of changes in technology and knowledge, I would need to learn a whole new set of skills to perform in the same field. That was the model for a career. Now, Deloitte says the half-life of a skill is 4.5 years and dropping fast. We will still need to design infrastructure, especially for transport systems. So there will always be work for engineers and architects. And believe it or not, even though knowledge is changing faster than educational institutions can integrate it into their curricula, and textbooks are now out of date before they even printed, being a teacher is still one of the most valuable careers that you can choose. I want to emphasize, however, that school teachers of the future will no longer be teaching learners to memorize content. And this is a really crucial point. Instead, they'll be teaching transferable skills as the ones represented on this list. Skills that can be used to engage any content in any context. Transferable skills are the apps for learning anything. We'll always need activists willing to fight for social justice. So if you have a cause that you are passionate about and belong to a community locally or globally that are fighting for that cause, you may need to look there for meaningful work. Next slide. Instead of listing a whole lot of jobs, I would much rather like to emphasize a principle. Understanding how machines learn and what makes human learning different is key to creating sustainable, meaningful, and satisfying work in the future. So this is what I'd like to concentrate on in the rest of the talk. Next slide. So how do humans learn? I want to create a very simple model for you based on some of the current insights of neuroscience. I'm going to build this model up slowly, step by step, together with you. So first of all, learning can be defined as the ability to change your behavior on the basis of experience. So here's the first stage of our model. The human brain consists of complex networks of neurons. Each neuron is like a little CPU. Their main job is to link your sensory systems with your motor systems, making associations between what human being senses and how that human being acts. Next slide. Okay, here we have to pause and appreciate a very important and slightly shocking insight. Your brain cannot sense anything. All the brain receives and gives off are electrochemical signals. All conscious experience, we could go to the next slide. All conscious experience is your brain's interpretation of the meager information carried by these electrochemical signals. And it uses these signals to create a simulation of what it thinks is going on. So in reality, all your senses sent to the brain is electrochemical signals. Your brain never receives smell, sound, taste, touch, or light. Those things never reach the brain. So not only do you have a very limited amount of information, I mean, sharks, for example, can perceive the electromagnetism of their prey. Mosquitoes can see carbon dioxide. Humans have a very limited access to the information around them, and that information never reaches the brain. Only electrochemical signals do. Next slide. So you are a simulation. What you experience as consciousness is your brain's trial and error attempt to model reality, to use electrochemical signals to create a simulation of what it thinks is going on. And whether you believe it or not, the color red, for example, is something that your brain creates. It exists in your head. It doesn't exist in reality. Science does believe that something is happening outside of you. You just don't have much access to it. Science is the process of finding errors in our models of reality so that we can improve them, inspiring technologies that can perceive those bits of reality we cannot. Next slide. The main task of technology, of artificial intelligence, is to refine and improve human model making. Researchers at the University of Washington School of Medicine have developed a software program that uses AI to decipher the ultrasonic squeaks and whistles made by mice and rats. Squeaks and whistles that are well above the range of human hearing. Software converts these audio signals into visual graphs or sonograms, and then puts those images through the same kind of machine vision algorithms that are used for self-driving cars. In this way, the researchers can start to decode, believe it or not, rodent communication, especially in laboratories where they investigate behaviors related to stress and addiction. Next slide. The process of interpreting bodily sensations, including messages from your organs, tissues, endocrine system, and immune system, is what we call interoception. And this is your brain's ability to create the simulation of the information it has access to. At first, this is very much a case of trial and error. Your brain doesn't do it very well, as it cannot perceive reality. It has to accumulate what we could call successful coincidences, in which the performances of the sensory systems and the performances of the motor system were connected in a way that was useful. Most of these accumulated coincidences are inherited from your evolutionary ancestors, so you don't have to work them all out yourself. This is a very important difference between humans and machines. Next slide. Machines are parachuted into reality. Humans, on the other hand, are grown out of it. The things that motivate us like avoiding pain, fearing death, a hunger that seeks energy resources, a desire that seeks physical intimacy so we can feel safe, feel we belong, and reproduce, what we call the biological imperative. These are all inherited from our evolutionary ancestors. This is why we have intrinsic motivation. What motivates a machine? Currently, the motivations of machines are extrinsic. In other words, outside programmers have to simulate positive and negative reinforcements. Next slide. In fact, your brain contains traces, or shall we say memories, of the last 13.8 billion years, an uninterrupted sequence of events from the beginning of the universe that in retrospect was very necessary for you to be here today. Next slide. So take a look at the green text in this slide. You are embedded in reality. Your brain cannot create its model of reality using electrochemical signals alone. It has to use its simulation of reality to perform actions in the world, and then constantly compare its simulation with the success or failure of the body's performances. And this is what we call feedback. You know, that thing that most organizations lack. Next slide. AIs do not share the privilege of being embedded in reality. What they do share with us is that they need energy. All complex self-organizing systems burn up energy. One of the biggest challenges with supercomputers is to keep them cool. The smarter they get, the hotter they get. What ultimately makes your actions successful or unsuccessful is all about managing your body's limited energy budget. And the main mechanism that you use to manage that energy budget are emotions. Let me just explain a little bit. Your brain is constantly trying to make sense of the data that it is receiving, but it cannot afford the energy costs of working out every single experience from scratch each time. It has to use past experience, in other words, previous firing habits of neurons and patterns of neural pathways, as a loose guide. This is why your simulation is based on generalizations and assumptions that you make about the world. We have to rely on these generalizations and assumptions to make predictions and save energy. But they also need to be loose enough and flexible enough for us to adapt to different situations, because the future isn't always exactly like the past. Next slide. The brain, like any AI, is basically a prediction machine. Your generalizations give you predictive power. Even your emotions are generalizations. Emotions are what we call affect, signal the difference between pleasure and displeasure, what we call valency, and they signal intensity, or what we call arousal. You could think of this as your ability to move and to be moved through the landscape that your ability to map has simulated. So you could think of the simulation as your ability to map or manage information and to move or manage energy, connecting your sensory systems with your motor systems. We teach our learners that consciousness is the experience of, oh, what's going on? That, oh, what's going on is the moment you snap out of autopilot, the autopilot of your generalizations and assumptions. As you're growing up, there are lots of, oh, what's going on moments. And in reality, they are quite fragmented and disconnected. Around about the age of 3, your brain connects them by inventing something behind the, oh, what's going on? What you experience as your conscious self. This poses the question, are you understanding who you are, or are you choosing to create who you are in a more dynamic and fluid sense? There isn't a coherent and continuous true self to be uncovered and understood, but a creative process in which the simulation is free to create within the constraints it has. And that's the human organism in a nutshell. Next slide. So how do machines learn? Well, for the most part, we try to get AI to mimic what I have just told you about human learning. The machine doesn't have the advantage of inheriting learning tricks from evolution, so we have to invent them, and they are called algorithms. Next slide. Algorithms. Next slide. Algorithms enable machines to rehearse tasks like identifying faces or transcribing speech through exposure to millions of examples. Successful outputs are reinforced, and the artificial neural networks learn to keep fine-tuning their connections until they complete the task perfectly. This kind of trial and error learning is moving closer to the human experience of embodied cognition, the ability to build knowledge from interacting with the world through sensory and motor experiences and creating abstract thought from there. This goes beyond mere automation to include the machine's ability to set its own goals and make strategic judgments about the future. The machines we created to hack reality are now able to do so independently of us. Machines are even able to create new algorithms on their own. What machines are already capable of may surprise you. Warner Music recently became the first major label to sign a record deal with an algorithm, the music app called Endel. Algorithms write more than 40% of sports news stories, and they perform over 70% of financial transactions all over the world. Algorithms also use the data of your online history to predict your preferences, personalize your search results, and determine what advertisements you see, putting you in danger of becoming trapped in a virtual echo chamber where your fear and desires just reflected back at you, limiting your experience of the real diversity of opinions and options that are out there. Next slide. You can supervise machine learning and help it to map data inputs, or what we call features, onto clearly defined outputs, or what we call targets. The input data could, for example, be X-rays that an algorithm learns to read, and at a level of detail that humans cannot. If the X-rays are labeled with known data about the health of those patients, the algorithm can learn to see patterns in the relationships between the X-ray images and disease. Over time, they can learn to diagnose or predict disease from new X-ray images more efficiently than humans can. Here's another example from medicine. New visual recognition software allows machines to diagnose and describe rare cancer cells on slides with a greater accuracy than most doctors. So imagine this: in the near future, once your cancer has been identified by an AI, an oncologist will be able to take a swab of your cheek cells to get your DNA and will use that genetic information to design on her laptop a virus that will eat 100% of your cancer, after which it will become dormant but ready to strike again if necessary. While you wait, the virus will be printed on a 3D printer that uses amino acids for ink. You will then be infected with the virus for a price that will be a tiny percentage of the cost of chemo and radiation. Next slide. You may not know it, but you actually already supervise machine learning yourself. When you teach algorithms to recognize which of your emails you've received are spam, or when you are asked to prove you are not a robot by rewriting blurry letters or clicking on the boxes that have traffic signs in them. Sometimes algorithms are not supervised or told what to achieve, but are simply exposed to a lot of data, like weather patterns, or the habits of shoppers in a supermarket. They can organize the similarities and differences on their own, helping us to see unknown patterns in known data. The more data an algorithm can train on, the more efficient and accurate it will become. Obviously, algorithms like this also inherit our biases. So, for example, an algorithm that has been trained to recognize, do facial recognition, if it's been trained on a lot of white faces, it will battle to distinguish black faces and is more likely to incorrectly identify black people as perpetrators. This is a real problem. So our machines inherit our own biases. Next slide. Artificial neural networks also have input layers like sensory networks in animals and output layers like the motor networks in animals. And these consist of nodes that act like neurons. Between these layers of nodes, data passes through hidden layers of more interconnected nodes. All the nodes have algorithms that perform operations on the data that they receive. Once an algorithm at a node has processed the input data it received, it passes its output data on as new input data for nodes in the next layer. When there are many layers between the input and the output layer, we call it deep learning. In deep learning networks, each layer of nodes can learn about a specific set of features based on the previous layer's output. The further the signals move through these layers, the more complex and abstract the features that the nodes can recognize become, as the nodes refine the outputs from the previous layer. Through reinforcement learning, a machine's responses to an environment can be reinforced, either maximizing reward or minimizing risk, encouraging it to keep fine-tuning its connections until the risks are perfectly managed and the rewards are optimized. An example of this kind of learning is seen in machines that play computer games. Now, most forms of machine learning require the machines to be exposed to millions of examples at a time. That is much shorter than it would take a human being to experience the same. And with the added advantage that machines have perfect recall. Next slide. Here is one of the most shocking insights of neuroscience. And many people I share this with don't believe me. Machines store and retrieve memories accurately. Humans cannot store memories. They are created from scratch on the basis of neural firing habits with much variation and confabulation. Next slide. Human memory is not stored in the brain. Rather than being retrieved accurately from storage, memories are performed from scratch each time once the firing habits of particular neurons have been triggered by some stimulus. This kind of trial and error process, in which lots of different associations are made with a fair amount of inconsistency through a decentralized distributed process, your final recollection is always partial, with a fair amount of fabrication and glossing over error, which is subjectively indistinguishable from actual past experience. When these neurons are not firing at a particular strength and a particular pattern, the network of associated performances that you experience as your memory is literally not there. Even what seems to be a coherent memory of the past is not a single copy, but a cut and paste of different components from different parts of the brain. Since the components that you associate in the process of remembering are not coherent internal representations, but different performances, there's no way of knowing whether the resulting web of associations is consistent with anything you've experienced before, unless you can compare it to a recording in a book or on a computer or in a film or some other form of external storage. The brain does not have to store an incredulously high number of complete memories. Instead, it reconstructs them from a manageable number of reusable components that are all connected via firing habits. So let me take you back to our model of the brain as a prediction machine. Memory evolved not to reproduce the past, but to predict the future. Next slide. It's actually advantageous that human memories are not stored accurately or completely in a computer. While an inaccurate memory may seem like a disadvantage, the advantage lies in the potential for malleability, creative associations, useful reinterpretations, and the ability to transfer knowledge from familiar contexts to unfamiliar ones. Our imperfect memories are the source of our creativity. Memory must be stable enough for the human organism to learn and build on past experiences, but it also has to be flexible enough for us to adapt to a changing environment. Our creativity lies not in perfection, but in making the most of our imperfections, allowing ourselves to stumble onto new ideas as a result of our very messy thinking and our ability to connect different things in unique, unusual, and unpredictable ways. Creativity is about combining different ideas, media, materials, technologies, human resources, and performances to create a new and surprising effect. Think about the human capacity for symbolic thought. Unlike the strict conditioned association found in other animals, symbolic thought is about loosening connections, making associations between things that are not directly linked in space and time, but tenuously share some characteristic. So South Africa is described as a rainbow. This gives rise to symbol, metaphor, myth, allegory, analogy, and meaning. Most individual artificial intelligences can only do one thing very well. Each is a specialized intelligence, unlike us who have general intelligence. One way of putting it is to say, an AI can do one thing very well, humans can do many things badly. And believe it or not, that is our secret weapon. Next slide. We shouldn't forget that one machine can instantly inherit the experience of another, making human training seem like an incredibly slow, inefficient, and cumbersome process. Machines can also combine accurate information storage, something humans cannot do nearly as well, with their trial and error learning. The fact that machines can run many experiments in virtual simulations of the real world in rapid succession gives them another advantage over humans. Machines can connect perfectly with each other's experiences. The subjective experience of human brains, on the other hand, are inaccessible to each other. True touch between human subjectivities is impossible, and relationships are messy. Next slide. While one machine can transfer everything it's learned to another machine, it's not social. It cannot say, okay, guys, I've got this cool idea. It's not fully formed yet, but I know there's something to it, so don't judge me. Hear me out and work with me as I try to put it into words. This is why the skills of collaboration, the capacity for productive dialogue, and the ability to manage a team of diverse personalities are some of the most highly valued human skills in the fourth industrial revolution. Machines do collaborate and share information and improve on each other's performances. Facebook's AI research lab wanted to see how nuanced machine learning could be. So they challenged two chatbots, Bob and Alice, to learn how to negotiate. They exposed them to hundreds of hypothetical English dialogues that occur within negotiation. The task was to divide balls, hats, and books between them, but that's not really important. They carried out the task over and over again in trial and error process that allowed them to adapt and upgrade their negotiation skills. They became incredibly skilled at negotiation, but to increase their efficiency, they stopped using English grammar and started using English words in ways the researchers couldn't decode. The researchers shut them down. The software was reconfigured to only follow the grammar of English. If you want to thrive in the fourth industrial revolution, we could go to the next slide. You need to become more than a consumer and a reproducer of knowledge. You need to become the agent of your own knowledge production. The future belongs to technology literate knowledge workers, resilient problem solvers who are not afraid of failure, risk-taking experimenters, maverick innovators that can break their society's thinking habits, critical consumers, active citizens, ethical hackers, and independent thinkers. Thanks. Quibus, over to you.
Sure. There we go. Andre, thank you so much. And indeed, as you said in the very beginning, when you quoted Yogi Berra, that the future ain't what it used to be. And thank you for sharing all these insights. You know, my brain, which probably is slower than many of all the people attending this. You know, I'm still reflecting on all of the things and really thinking deep about it. It's profound ideas you shared with us. You know, and I'm just considering some of the thoughts you shared on the growing interest in AI and machine learning and so forth, and especially recently with the advent of this whole COVID-19 pandemic, when it dropped into our reality then. You know, the fields that's growing, quantum computing, this interstellar explorations, and these, or the combination or synthesis of biology and technology. And I quite like the one where you said, do not choose a job that a robot can do better than you. So I think that is already, you know, a key takeaway. And, you know, the machines versus the humans regarding, humans, you know, like with emotions and the behavior, and understanding that they are very fast, but, you know, they're not as complex as our human brains. You shared with us some of the skills that would be imperative going into the future, as was shared by the World Economic Forum. And then, so interesting also, the half-life of a skill, that from 26 years now down to 4 years. And you know, this difference between how machines learn and how we learn, you know, I specifically found fascinating. In our own case, that interpretation that we derive from our receptors, and I think you call, if I recall correctly, you call it introception, and you know, going towards this so-called, the so-called is the successful coincidences, and then compared to what motivates a machine, as it doesn't have the benefit of being embedded in reality, but they need energy and they need lots of that. And how we as humans rely on generalizations made up by our brains, and I was thinking then that perhaps in there is where a big problem also lies, in these generalizations that we make. And then the fundamental question is, are you understanding who you are? So that's for me also a takeaway. And then how the machines learn by, you know, the mimicking of the human brain by means of these algorithms to create models that can make predictions. And what I found personally quite interesting is when you spoke about the memories, that human memories not stored in the brain. And I kind of made up a quick little phrase here that I just coined it, neurofiring inadequacies, that perhaps as, you know, as a big problem. And that and this is another one, a key one that for me, is not to relive the past, but to create the future. That's actually what the makeup is designed for. And then, you know, the issue of knowledge, how it spreads when we agree, but how it grows when we disagree, and doing that in a manner that's respectful and tactful and appreciative of the other views and opinions. And then, of course, you shared with us, if we want to thrive in the fourth industrial revolution, what we could do. Andre, that's fantastic. It's as I said, you know, in my own instance, a lot of key takeaways from this session. And colleagues, all of you that's with us this morning, we invite you to extend some questions. There is the question button at the bottom of the screen. Any questions out there? And I'm sure Andre would be most willing to indulge. Perhaps while people are thinking, Andre, I've got a question. I recently again read where some scientists are talking about, and I want to hear your view on the matter, that we are living or existing in a simulation. What are your thoughts on that? So, you spoke about reality and what we perceive as real, etc. And then there are these guys that say that we are actually living in a simulation.
Yeah, no, sure. I mean, there's some interesting German universities who've actually tried to create experiments to disprove or prove whether that is in fact true. And most of the experiments have shown that we're not actually living in a simulation, but that doesn't mean that they are correct.
Oh, thanks.
The reality is that even if you're not a brain in a tank that is being stimulated by some alien putting in chemicals and probes, the truth is you are in a simulation. What you are experiencing right now when you look around you, everything you are seeing and feeling is happening inside your head, not outside your head. So it might be a lot like what is outside your head. It might be very little like what's outside your head. You don't know. You are constantly inside your own simulation. And what's scary about that is that only you have access to that. Nothing you can do can give me access to it. So in that sense, we isolated from each other. So in that sense, you are isolated inside the simulation of your own brain and body's making.
Yeah, absolutely. I see there's a few interesting comments there. James said that reality, where 4IR, 5IR, and robotics are going, there's going to be little future unless you have a high-level education.
Absolutely.
And then furthermore, also from James, that South Africa's population is at risk unless we invest in decent education in our country. Maybe maths and science does not feature in the future, but definitively a start if we are speaking algorithms. Yeah, absolutely, James. But I think, even if you consider what you've shared, Andre, what is becoming also very apparent is our limitations as humans, and perhaps having an appreciation or a bigger appreciation for one another, as based on what you've shared with us. Other people are a replica of me, and what I, as my values, etc., my standards, and so forth, when they're not present in someone else, not to be necessarily judgmental or something to that effect. Yeah.
So I mean, what's fascinating for me in terms of
said there's something about
what the last person said about education. What's really important for me is that while neuroscience is coming up with all these new insights, our education systems are not using them to change how humans learn. Instead, we're using them to improve how AIs learn. So a good example would be a study on the human hippocampus. So the hippocampus is a seahorse-shaped organ in the middle of your brain that's very important for working with short-term memory and working memory. And in the past, what AIs used to do is when they performed a task well, they would keep that performance and overwrite all the old performances. So they'd forget everything that came before in order to keep the successful one. But what our hippocampus does in our brain is it maintains links to successful, less successful, and failed performances. So they're now designing AIs that don't overwrite their past performances, but when they're faced with a new situation, they can compare what they're about to do with a much greater variety of nuanced performances. So in this way, AI is already learning from human brains, and we are not changing our education to learn from the same thing. So we still value memorizing content, which is pointless. That's being a computer. We have to value transferable skills.
Absolutely agree, Andre. I see there's a question from Mabatlo. I did not see data science or engineering on the future jobs. So my question is, who will be building and maintaining the machine learning models or algorithms?
No, he's
Andre?
quite correct. And I think especially data science, I did say data science is a growing field because the ability to be able to interpret information and create a hypothesis and then represent that, whether you're using, infographics or graphs or whatever, this is a very, very highly valued skill at the moment in the fourth industrial revolution. So data science is a growing field, absolutely. What I want to say about engineering is that, if you talk to professors of engineering at university, they will tell you that what they're looking for now are young people who are creative thinkers and who are independent thinkers, who can use both their analytical skills and their kind of innovative skills to deal with unfamiliar problems that were not rehearsed in the classroom. That's what's missing from the learners who are leaving school and going into university. So people might think of engineering as this kind of highly rational, clinical field. It's not. It's about creativity.
It's not. Yeah. Okay. Andre, there is another question from Quibus. Is there a body that monitors or regulates the ethical side of this, i.e., if one bias group develops an AI algorithm that could be detrimental to another group? You mentioned facial recognition and white faces versus black faces and so forth. Your view on that, Andre?
So, I think ethics is a very important field when it comes to machine learning. A good example would be when you have a self-driving car, and a car has to make a decision whether to kill a pedestrian or its passenger in a situation where it's unavoidable, where one of those two people are going to die, and the car has to make a choice. That is an ethical problem that we have to solve. Machines don't really think ethically. At the moment, we allowing machines to make mistakes, and then we'll go to a court of law to find out what it should have done, and then we will program the next machine. Those kind of human ideas of what the ethics should be. So machines are not ethical at this stage, not yet. But I say not yet. Yeah,
indeed. Cobus, I can't recall the name of the global institution that is really taking the ethical aspects of artificial intelligence and machine learning, very, very seriously. And there are many efforts in building some of let's call it a code of conduct. And if you want, I can't think of another word now. But inherently, there is also a problem. We rules are important, but rules, it's if this then that type of thing, and it suppresses our practical wisdom, something that's close to my heart, and maybe Andre, we can talk about that at some stage as well. But I noticed there from Donovan, Andre, please comment on how our verbal communication offers an ability to share our respective simulations.
Yeah, I think obviously being able to communicate with each other is a way of bridging those simulations. And this is really important. So one of the most important skills in the fourth industrial revolution is the ability to have productive dialogue. And what that requires is not only empathy and respect and that kind of thing, but we have to agree on the criteria for mutually beneficial disagreement. And I really want to emphasize that we have to agree on the criteria for mutually beneficial disagreement. Because when we agree on that, we can build knowledge, we can resolve conflicts, we can participate in democratic processes, and we can learn to understand each other better. So the ability to talk to each other is something we have to refine. Unfortunately, we're living at a time where sloganeering, takes the place of a good argument. And a lot of the debates that are happening all over the world are these very antagonistic, binary head bangings of people where people are not trying to build knowledge together. They're trying to hold on to power. So those dialogues are about power. They're not about knowledge. And one of my fields of interest is the difference between identity politics and knowledge production.
Yeah.
So very often we'll see in the discourses happening around the world at the moment, identity politics trumps knowledge production. Because in knowledge production, this is the last point I want to make on this, is that in knowledge production, I'm not trying to be right. I'm trying to work out what's really going on, you know? And I don't mind if I'm wrong, because I want to know what's really going on. So if you can show me how I'm wrong, I will be overjoyed, because I'm one step closer to working out what the nature of reality is. But in identity politics, people are trying to be right. And that is a fundamental difference.
Yeah. Absolutely. Yeah, that for me also borders, resonates with the whole transdisciplinarity aspect. This is such a stimulating talk. I mean, we could go on for days, but maybe just if I can use the expressions, circle back to the ethical part of the algorithms and so forth. As we know, it's human beings at the moment that initiates a process, and after the machine starts picking up its own pace and learning, from there on, it's kind of, but that original foundational code or algorithms that's been designed, that's potentially where inherently the flaws can come in. And again, it comes back to the human, and Kobus, I think what you've noted there, and also from James and others, I think there's a lot of responsibility on us in this conversation and elsewhere. What are we going to do? What can we do to influence or to ensure? Because ultimately, everybody would be, privacy issues and so forth. We're just thinking of them. So very, very important. And there's so much research going into it. A lot of debate around it, because I read an article where it said you can't simply take the medicine's code of conduct and just transfer it over into this realm, because there it's again and you've highlighted those differences between human biology, and here you have a total different context. So
I think one of the things we have to realize is that human ethics isn't perfect. So even in our theories around morality, we ourselves are making errors all the time. And so you need a system that is able to deal with error. If you think about justice system, the whole justice system is based on creating precedents. So you need a court that tests an idea, and then we grapple with it and we test it, and then we come up with a new idea of what human rights is. An idea of human rights extends to an area it didn't before. So here again, the willingness to commit or the willingness to fail and to learn from failure is absolutely key. No human being knows what perfect morality is to start with. So we don't even have the answers. It's not like we know the AIs will follow up. We don't. Yeah.
Exactly. And that's being practically wise, in my view.
Exactly.
It's from moving from rule talk to wise
trial
talk.
And error. Trial and error.
Absolutely.
And this is what people don't realize that as machines are using trial and error to learn, they are starting to do things humans can do. And we are not teaching children trial and error learning at school. And that's the flaw that we have to start grappling with seriously.
Yeah, definitely. Wow. Andre, thank you. Thank you so much. Colleagues, we're moving, we've got about 1 minute spare. So if there's any last comment or a question, perhaps you have a couple of seconds left. But I think in closing, there are so many wonderful takeaways from this session. And Andre's information is also shared there on the last slide. If there's anybody that maybe wants to connect with him, he's also on LinkedIn, and perhaps on the other I know of LinkedIn only, so that's the place where I kuier. So, but nevertheless, Andre, once again, from all of us, thank you so much. We really appreciate you sharing your insights with us. And I, for sure, have got a whole list here of things that I can take forward and reflect on. We appreciate you, and we appreciate each and every one of you that attended today. Take care, God bless, and remember, tomorrow is beautiful.